Okay, so in this video, we're going to go over a lot of the Newton's first and second law example problems that we didn't get to in class today. So the first problem that we skipped was this one, making a previous problem a little bit more quantitative. So Liz is in an elevator, so she gets in an elevator ground floor or first floor. From the first to the second floor, the elevator accelerates. And then she coasts going upwards at constant velocity until the fifth floor, and then from the fifth to the sixth floor, the elevator comes to rest. And we saw in class that the normal force, or her apparent weight in the elevator, it goes up during the accelerating part, because the normal force has to be bigger than mg in order to accelerate her upwards. And then the normal force is less than mg when she decelerates back to rest, when she rides at the top floor. So this question asks, what is the minimum reading on the scale? And this happens during the deceleration phase. So this happens when n was less than mg. So when she arrives at the top floor. That's when she'll have the minimum normal force. So we're given some numbers here to actually solve for what that acceleration is. So we're told that the elevator is moving at 6 meters per second. So when the elevator is moving between, from second to third to fourth to fifth floor, the elevator covers 6 meters, which is the distance from one floor to the next floor, 6 meters per second. So that's going to be her initial speed. Okay, we're gonna look at her deceleration from the fifth floor to the sixth floor. So her initial speed is going to be 6 meters per second. She's going to come to rest. And the delta y that she travels is 6 meters. So in going from the fifth floor to the sixth floor, she's traveling upwards, but she's slowing down. She's going from 6 meters per second down to 0. So we have a kinematic equation for this. V final squared is V initial squared plus 2a delta y, or minus 2g delta y. If we plug in 0 here, 6 meters per second here, and then delta y is 6 meters, we'll get, oops. Ooh. So one bad thing about this, I said that the acceleration is g vertically downwards, but no, there's a tension in the elevator cable in addition to gravity, and so it's the combination of the two that will make the acceleration something that we don't know. So let's just leave this as plus a. The acceleration is what we're solving for, and what you get is a is minus 1/3 g. 36 over 12 times g. Yeah, you get minus 10/3 meters per second squared, and we're gonna say g is 10 in this problem. Okay, so this is Liz's acceleration. Now, a free body diagram of Liz during the deceleration looks like this. It's mg down, as always, and then she has some normal force that's less than mg, right, in order for her to slow down. And it's the sum of those two pieces. So the addition of these two pieces, of these two vectors, is going to point downwards, right? Her acceleration is downwards at 1/3 g, 1/3 g vertically downwards. So the absolute value of a is 1/3 g. Okay, so in order for the acceleration to point downwards, this needs to be bigger than this. Okay, it's mg minus the normal force is going to be her mass times her acceleration, 1/3 g. So here we're using some of the forces as mass times acceleration, and we're choosing the downwards direction to be positive. Okay, so overall we have a positive number equals a positive number. Okay, whenever you write down an equation, you should know whether you're writing down positive equals positive or negative equals negative. You should never write down positive equals negative. Okay, so the normal force, if we solve for the normal force here, we get m times g minus 1/3 g, or 2/3 g. So the minimum normal force is 2/3 of her weight, 2/3 of her normal weight, mg. So this is 2/3 times, and her normal weight, I think, is 800 newtons. When the elevator isn't moving, this is her weight. So this is mg. So this is 2/3 times 800 newtons, or 560 newtons. Okay. So we solved for the tension in the string here. Let's look at this problem. A box is being pulled with a force that is applied at some angle. And the angle is 30 degrees relative to the horizontal. And the box has no friction right here. Find the acceleration of the box and the normal force exerted by the ground on the box. So we're going to draw a free body diagram, and our object is going to be this envelope-looking box. And one of the forces is going to be this F pull. So we'll just use the FP because it was already labeled for us, FP. Then the ground is pushing up on this thing, so there's going to be some normal force there. And the box has some gravitational force acting on it. Just the Earth is always pulling down on every object near the Earth. Okay. So normal force up, mg down, and the pull. So we're done with our free body diagram. Now we want to apply Newton's second law, and let me introduce this coordinate system. So we're going to say the sum of the forces is mass, the mass of the box times the acceleration of the box. And so we're going to split this into two pieces. It's an x equation and a y equation. Okay. Now the box, so you can actually, so this mg is about equal to 100 newtons. Right? M is 10 kilograms and G is about 10 meters per second squared. So it's 100 newtons. This pulling force is not going to lift the box off the ground. If you take the vertical component of the pulling force, you just get 20 newtons, right? 40 sine 30 degrees. So the box is not going to lift off the ground, which is why actually we kept this normal force in there. But this also means that the acceleration, the y component of the acceleration is going to be 0. Okay, the vertical parts of all these forces are going to cancel. So basically, n is just going to be big enough in order to keep this thing flat. It's not going to start flying because the pull is not big enough. And the thing doesn't go crashing through the ground because the normal force is there. So the normal force is just how big it needs to be to keep this thing flat on the ground. There can be an acceleration to the right, and there will be because there's a horizontal force to the right that's uncompensated by anything pointing to the left. There's no leftwards force. So this piece is going to be non-zero, but the y piece is going to be 0. So let's start with the y direction because that part's equal to 0. So presumably it's easier. We can get some information out of it. All three vectors have a non-zero y component. Looks like 2 of them have a positive y component. One of them has a negative y component. So we have n plus fp sine theta. I'm just going to leave 30 degrees as theta for now. Is equal to, or minus mg is equal to 0. So that's the y components of the 3 different forces. 2 of them are positive, one of them is negative, and they add up to 0. Okay. So we don't know the normal force, and we don't know the pull, or sorry, we do know the pull, and we know theta. So we can solve for the normal force. We know this one, we know this one, we know this. We know all those checkmark things. So we can solve for the normal force. Normal force is mg minus fp sine theta. Okay, then we can plug in numbers to get, so we'll get about 100 minus 20 newtons. This is about 80 newtons. Okay. Now for the x direction, looks like there's only one force that has a non-zero x component, right? This has no x component, this has no x component, but Fp has a non-zero x component. So Fp cosine theta is equal to m times ax, x component of the acceleration. So the acceleration of the box is Fp cosine theta over m. Right, and plugging in numbers, looks like we have 40 times root 3 over 2 is 34 newtons. Divided by 10 kilograms is about 3.4 meters per second squared. Plugging in the numbers. Okay, so we solved, so the acceleration, which is a vector. So really these are vectors, right? This is a vector and this is a vector. We should really express our answer as a vector. So the acceleration is 3.4 meters per second squared to the right. And the normal force is equal to 80 newtons upwards. So really expressing our answers as vectors, we should indicate the direction as well. Okay. That one in class. Did that in class. So in class, we just got that the tension decreased because M1 is moving down. But this is the way you're going to solve for the acceleration. So M1 and M2 are two different objects, so we can apply Newton's second law separately to both of them. So for M2, in the horizontal direction, there's only one force acting on it, and that's the tension. So this is the sum of the forces on M2 in the horizontal direction. Sum of the forces on M2 x is equal to M2 times AX. So that's this equation. And then the other equation is the sum of the forces on M1, but in the downwards direction. Call this. So if the x direction is to the right here, we can kind of continue that line and say, well, the plus x direction is going this way down here as well. So the forces on M1, the x components of them is here. And those two accelerations are equal because the rope that's tying these two together forces each mass to move with the same acceleration. Okay, they're always moving with the same velocity, so the changes in velocity with respect to time are also the same. Okay, so when you set up those two equations, you get two equations for two unknowns. We don't know the tension and we don't know the acceleration. But written this way, it's easy to solve by elimination. We can add the two equations together. So that means add the two left-hand sides together and add the two right-hand sides together. And when we do that here, and this is common with tension problems, what happens is that the t's cancel out. The t and the minus t cancels out. So that's one of our unknowns that just disappears. And we're left with just one unknown, the acceleration that we can solve for. So we can solve for the acceleration, which is downwards for M1 and to the right for M2. And this is the magnitude of that acceleration. Okay, so we did that one. Done. Let's try this one. Two total forces act on the box to the right. Only one is shown. Now you got to be really careful. This is an acceleration which doesn't belong on a free body diagram. Okay. Really, this should be written somewhere else. Okay, the acceleration is down and to the left at some angle theta. Okay. So we're told that we have two forces acting on an object gives you that acceleration. So the force, the second force, needs to point kind of really left and down. So this is what F2 looks like. Because when we add in F1 to this, so F1 plus F2, it gives you the direction of the acceleration. Okay, so this would be the net force direction. And really, you shouldn't be putting this on the free body diagram, but the net force also points in this direction, or the sum of all the forces. So F2 needs to point down and left, or it needs to have negative x and negative y components, so that when you add F1 to it, So you note a vector that when you add something pointing to the right, you still have something pointing down and to the left. Okay, for F net. So this needs to be F2. It needs to point even at an even bigger angle than F net. Okay. The ball moves along a circular track on a horizontal tabletop. As shown, there's a bird's eye view. Suddenly, the track ends and the ball exits the track. Which path will the ball follow after leaving? So this is a sneak peek for circular motion. It turns out that in order for the ball to stay on the track, it needs to change its velocity constantly. So if this is the initial velocity vector and this is the final velocity vector, then the acceleration needs to point towards the center of the circle in order to keep the direction changing. Okay, but as soon as the ball exits right here, there's no more track keeping it to change the direction of the ball. So the ball is just going to keep going along its line of sight C. Okay. Three blocks are suspended. Are these three blocks in equilibrium? So again, with these rope kind of problems, if this block is moving upwards, then this block is moving downwards, and vice versa. So we're going to call this the positive direction. Okay, this is kind of a one-dimensional problem here. Plus M1, M2, and M3, but they're all the same mass. So for M2, if we look at a free body diagram for M2, there's this tension that's pulling vertically upwards on it, and there's M2G pointing vertically downwards. There's something similar for this one. There's a tension pointing upwards and M3G pointing down. So if we set up a free body diagram, or sorry, a Newton's second law equation for M2, we have the sum of the forces on M2 is equal to M2 times its acceleration. And this is a 1D problem where upwards is positive. So the tension is positive and M2G is negative. Those are the two forces acting on M2. This is M2 times its acceleration. And then for this block, now we're going to choose the downward direction to be positive. So the sum of the forces on M3 equal to M3 times its acceleration. And here down is positive, M3G minus T. So M3G is in the positive direction, tension's in the negative direction. So those are the addition of the two forces equals M3 times its acceleration. Now these are the same acceleration. If M2 is moving up with a positive acceleration, M3 is moving down with that same positive acceleration. Okay, so the whole reason we did this and this, changing the direction for positive, was so that we could use the same A for both these two equations. So if we add the two equations together, meaning we add the left-hand sides and we add the right-hand sides, the T's cancel out and we get M3 minus M2G is equal to M1 plus M2 times A. But M3 and M2 are equal to each other, so this is 0, is equal to the acceleration. Okay, so notice how even though M2 is higher than M3, it doesn't really matter for problems like this. It doesn't matter that M2 is higher than M3 or not. It's the same mass here, so there's 0 acceleration. There's 0 acceleration for this one as well. So all three blocks are in equilibrium. They're not moving. Okay, but if M3 were just a little bit bigger than M2, then there would be a positive acceleration here. If M3 had a smaller mass, then there would be a negative acceleration. M2 would go vertically downwards, and M3 would go vertically upwards. Okay, so we just actually, so because they're all at rest, the tension needs to exactly balance. Okay, so if we take equation 1, for example, from before, and we use the fact that the acceleration is 0, we get T minus M2G is equal to 0, where the tension right here is M2G. So this tension is M1G. And this tension is the same thing as this. So all of the tensions are equal. Okay. Find the acceleration of the system. So now we left M1 and M2 general here. So we actually already did this. So it's the same procedure as before. And what you get is that so first of all, if this is our positive direction, this is A positive, then you get A is equal to M1 minus M2 over M1 plus M2 times G. So if M1 is bigger than M2, then the system will have positive acceleration. If M2 is bigger than M1, then it will have negative acceleration. So would it affect your answer if M1 were higher than M2? Yes, it matters which one. So yes, it affects the direction. And in terms of our answer is okay, but A would be negative. So in other words, our answer still applies whether M1 is bigger or smaller than M2. But we have to go back and reinterpret our answer based on those two different cases. So if M1 is bigger than M2, acceleration is positive, means M1 moves down, M2 moves up. Okay, and we're done with the example problems. On to Newton's third law tomorrow.